Okay, so did you try to get to the homework, chapter 10? I'll put that up. Are you able to get that? So with your workbook, you should have signed up for online access to the online text, and then you would click on Module 10. You're going to need this for Wednesday to do the homework. So Module 10, and then Homework Student, and this is where the homework's going to come from. This is not in your Module 10 isn't in your workbook. So you're going to have to get this homework online. Did anyone try to do this and was unable? No? Okay, then I'll just assume that you're all able to get to here. Any questions? Okay, good enough. I'll plug this in. Wait.
We have to do that entire all of it, or do we?
No, just like normal. I'm posted on what Blackboard. This is where it will come from. This is just like the homework in the workbook, but you don't have it in the workbook. Yeah. So just like all semester, you'll find the problems that you're going to do on Blackboard. I have not posted those yet, so I'll try to post those this morning. In the meantime, you have lots of web work to do. Okay? I doubt that you've finished all the homework, all the web work. So work on the web work until I get those numbers, the problem numbers posted. This is where you'll find it online. Rationalreasoning.net, Module 10, homework. Okay, today in recitation and Friday in recitation, you have a post-test, which you should not have prepared for, don't worry, but you want to do your best because I will give you, depending on your performance, I'll give you extra credit on exam 3. Okay, so depending on how well you do, I'll have some kind of sliding scale of percent added. If you do really well, you may get 2% added to your exam 3 score. Okay? If you do mediocre, maybe 1%. If you don't do well at all, then we'll keep your exam 3 score the way it is. So just do your best, but don't worry, you should not have prepared, okay? And that will be both today and then Friday for recitation. Okay, so we're finished. We were talking about identities. Let's see. We had our list. So this is a kind of the very most basic identities. Remember what an identity is. It's true for no matter what value you put in for the angle. Okay? So since we have all these different relationships, sine, cosine, tangent, cosecant, secant, cotangent, what happens is we get this explosion of all these different identities in trigonometry based on those relationships. Okay? And based on messing with the angle. Okay? So these are the very most basic ones, but from these come many, many, many more. Okay? And remember, again, an identity is an equation that's true for no matter what angle you put in. You don't solve it to figure out which angles make it true. It's true for every angle. Okay? And that's the idea of an identity. So here's an example of... So at the end of class, we worked through these. You worked through these, and you were given this expression, and you were asked to find what does that expression equal to. Another kind of variation on that is what's called to prove an identity. Okay, so really, when it comes down to it, if any of you continue in math, like you're a math major, you'll find that really what math is about is proofs. Okay, is proofs. And so we should start now learning how to do a proof. So if it said, just ignore all this. You don't need any of this anymore. Okay, so I'm going to, this blue, what I've written here in blue, is what we're going to prove, okay? So this is what this is saying is this is an identity. This is an identity. Prove it to be true. Prove it to be true. So here's what lots of students do, and in a case like this, they'll start, and their first step will be to write this out, and then they'll find what this equals to, and then they'll do a step on this side, and then they'll keep taking steps on the left and the right, and say they're equal all the way down, and then in the end they'll have say sine x equals sine x. And so, therefore, it's proven. Okay, so while that has all the work that you would need for a proof, that's not a good proof. Why? Because you started off by assuming the very thing you were trying to prove. So you can't do that. So this has to be your conclusion. This is not the given. This has to be the conclusion based on the work that you do. That's what a proof is about. Concluding that to be true, not assuming it's true from the beginning. Does it make sense? So just starting with this equation and working on both sides and calling them all equal until you get something simple that's equal is not a good proof. So instead, what we want to do is we want to pick one side and make a chain of equality to arrive at the other side. So for instance, we start with A, which would be one side of this equation identity, and using algebra and other identities, we say, oh, that equals B. And then using more algebra and other identities, we say, oh, B equals C. And then we keep going like that until we arrive at Z. Conclusion, therefore, so 3 dots like this means, therefore, what's true? A equals Z. That's a good proof. That's one type of good proof. You start with one side, and you say, okay, by things that we already know, that equals A equals B. And then using algebra and other identities, B equals C, etc., until you arrive at the other side of the original thing you were trying to prove. And by chain of equality, if A equals B equals C equals D, equals Z, then therefore, that's the 3 dots in the triangle, therefore, conclusion, A equals Z. That's a good proof. Does it make sense? Okay, but don't do what lots of students do. Again, start with this statement and then work down both sides, calling them all equal until you get something simple that's equal, and then say, therefore, proven. That has all the work that you need, but it's not good form. Okay? So, which side to pick? So, generally, you just pick on the side that you can do something with. The one that's more complicated. That's kind of the rule of thumb. Something that's more complicated that has kind of would be easier to manipulate and change around. So which of these two? So if we're going to prove this right here, which of these two sides do you want to work on? Left or right? Yeah, you might say left. Actually, in this case, either. So either we could work on, but yeah, left is fine. So here we go. We say proof. And if we're going to start with the left, we're going to say 1 minus cotangent x over cosine x equals something that we know either by identities or just by algebra. So the most common techniques that you'll see here is you'll be adding or subtracting fractions, and so you'll do a common denominator, or you may take a fraction and pull it apart into 2 different fractions. And then the other technique is to change everything into sines and cosines. Change everything into sines and cosines. So what can we do with this? So we've got one big fraction, but there's a subtraction in the numerator. So what can we do? What do you want to do, what? Right. Okay. So we can actually kind of reverse. It's like, if you were subtracting fractions, you get a common denominator and you make one big fraction. So this is kind of like going into reverse. We're going to pull these fractions apart, each with the denominator what? Cosine x. So what's our numerator, the first numerator? 1. What's our second numerator? cotangent. But let's go ahead and also change that into cosine over sine. So you guys pick the left side, and now we've got something that we know that's equal to, just by subtracting fractions, actually kind of reversing it, pulling them apart. Okay, what's next? Equals? So what is 1 over cosine x? Secant, okay, it's looking good, right? And so we got a subtraction. This is looking good, like it's heading towards our target. So here's secant x minus. All right, so what can we do with this? How can we simplify one fraction divided by, say, another fraction? Yep, invert and multiply, right? So dividing by cosine is the same as multiplying by? Multiplying by what? 1 over cosine, right? So dividing by cosine would be the same as multiplying by 1 over cosine. Okay? So we got some more work to do. Where do you see there? Yeah, cosine over cosine is 1. So those two go away. And then what do we have? 1 over, which is cosecant. Our definition of cosecant is 1 over sine. Lo and behold. So we started with this. We know it's equal to that. We know that's equal to this, which is equal to this. Therefore, we could rewrite the statement. I'm out of room. But so you could say, therefore, 1 minus cotangent x all over cosine equals secant minus cosecant. Because A equals B equals C equals D, therefore A equals D. Because they're all equal. That's good proof. So you start with one side, and then you work on that. So another technique you can do is, so we're going to start with the left side. You can do some side work to start with on the right side. Like, take a couple steps on this over to the side. And that kind of gives you a bigger target to shoot for when you work on the, say this case, the left side. So if you take that right side and do some side work and find a few things that it's equal to, then you have a bigger target to shoot for by working on the left side. But we didn't need to do that here. We were able to get it. Okay, questions on identities or proving identities? Yeah, Alex. Sure. Are you saying you want me to, or are you saying is it possible? Yeah, what would you do? So you want to start with secant x minus. So instead, we could have started with this side. What could you do first on this? Right, change this to sine and cosine. So let's do that. And what would it be when you change it to sine and cosine? Beautiful, okay. What are we going to do with that? Okay, so what common denominator would you have? Yeah, so you need cosine times sine to get a common denominator. So we'd have sine x over cosine x sine x minus cosine x. Did you catch that step? I kind of did 2 in 1. So I made a common denominator, that's times, not minus, it's times. So I made a common denominator cosine times sine, and that would mean sine minus cosine in the top. Is it okay? All right, now what? So we kind of have to look at where we're heading here. We need this, so it kind of looks like the form of this, right? But what do we need here? We need what? We need 1. So what could we do here to make this equal to 1? Not cross out. You're not crossing out because this is minus. You can't. This is sine x minus cosine x. You can't cross those out. So we could take 1 over. In order to get closer to this, we could take 1 over sine x divided by 1 over sine x times this thing. And then we'd have our, but then this would be multiplied by both. So then there would be the 1 minus cotangent. Cosine divided by sine is cotangent. And then 1 over sine times this is cosine. There it is. I went fast. Did you catch it?
How would you get the 1?
I multiplied top and bottom by 1 over sine x. So sine x, that was my goal, was to get 1.
Right.
So I know to get 1, I got to multiply this by 1 over sine x. So I multiplied everything. I got to multiply everything by 1 over sine x.
Okay.
And so there's 1, and then cosine x times 1 over sine x is cotangent, and your denominator becomes just cosine. So that's valid too. So on this particular one, you kind of could start on either side. But if you get you have a fraction or a difference or something, and it equals, they say equals sine x. Well, you're definitely going to work. It's going to be hard to start on sine x and get to something more complicated, right? So you're going to pick the side that's more complicated, that gives you the chance to actually do something, manipulate it. Adam.
So even though we're not assuming that what you prove is actually true,
Right?
we do whatever we can to manipulate it to get into that.
You pick one side. You pick one side of the two, and then you've got all your algebra and all the other identities to use to work on that, to get it to be the other side. Right? So again, it goes back to start with one side, call it A. Use identities in algebra. Equals B. Use identities in algebra. Use identities in algebra. And then, in the end, you're shooting for the other side, therefore A equals Z. No, but if it's giving you, it says prove this identity, it's going to be right. It's going to be true. It's not going to be maybe true and maybe not. If it's a problem that says prove this identity, it will be a true statement. And if you can't do it, then it's not the problem's fault. It's your fault. Okay.
I'm having trouble with the 1 over sin x times the sin x minus cos x.
Okay, this is distributed property, right?
Say that one more time.
A times B plus B minus C equals what? AB minus AC. What's 1 over sine times sine? So I'm going to distribute, right? Distributed property. What's 1 over sine times sine? What's 1 over sine times cosine? Cosine over sine, right? Which is cotangent. And I chose 1 over sine just to get a 1 there. That was why I chose it. Because I knew that if I multiplied sine x times 1 over sine, that would make that 1. So you're doing the distributed property. Other questions? Okay, so that's identities. You got lots of practice in web work. Web work doesn't allow you to write up a formal proof, but you'll do lots of questions like these on the left here. Will it give you one side of it? So basically, you're doing the same work as you would do in a proof. Because it give you one side, and you have to figure out what the other side is. Okay, and then in those problems, often it'll say something like, I get lots of questions about this. So it'll say, solve, do you guys remember what this one equaled? Was it just sine in the end?
I think it's sin x.
Okay, so they'll give you this, and they'll say equals f of x. And then the answer box will be f of x equals what? So you'll work on that, and you'll get a function, and then you're going to enter in that function. So in this case, you'll enter in sine x. Or suppose the answer was 1 over cosine. Okay, so suppose you work this whole thing out, and you get 1 over cosine x. Then in the answer box, they'll say something like this. They'll say, your answer should look like this, 1 over f of x, where f of x is So if this whole thing turns out to be 1 over or secant or 1 over cosine x, then they'll say, oh, your answer should look like this. And there it is. It looks like that, right? Where f of x is what? Cosine. You see? So the answer you'll enter in is 1 over cosine x because of the way they've asked it. But that thing equals 1 over cosine. Okay, so any questions on identities? Okay, we're going to move on to vectors. So you guys are all engineering majors, right? Vectors are crucially important in engineering, okay? Cool stuff. And we've got a whole week to work on it. Or almost a whole week. Okay, so the first thing let's talk about is what's called vectors versus scalars. So before, we were operating in the world of scalars. We just never called it that because there was nothing to compare it to. Okay? But when we talk about vectors, then we have to qualify that. We have to say, oh, hey, look, this math world that we've been dealing with has really been all about scalars. And so what is a scalar? So a scalar is a quantity. So these are both now types of quantities, right? And we said a quantity, remember from week 1? What was a quantity? Does anybody remember? Everyone should remember. What is a quantity? Michaela's got it. How about over here? Yeah. Right. So it's something about an object, a characteristic, an attribute about an object that we can measure. So to this point, we've really been dealing with scalar quantities, which are quantities that just have an amount, magnitude, but don't have necessarily an associated direction with it. Okay? So examples of quantities, attributes that don't have a direction associated with it. Temperature. Right? So temperature is just, it's 73 degrees Celsius, but it doesn't, there's no direction associated with it. What's something else? What other kind of quantity does not have a direction associated with it? Someone said time, okay? Weight actually does, because weight is a force, and the direction of weight force is straight down to the ground, okay? So actually weight does. Mass is a good one. So mass, I heard mass, time. These are good examples, okay? So yeah, mass, time elapsed. They don't have a direction in three-dimensional space that we can talk about. Volume is another one. These are scalars, no direction associated. Okay, vectors then are quantities, they're attributes of objects that not only have a magnitude, but then also have a direction, an associated direction. Okay, so someone said weight. That is, more generally, force. So if I told you I'm going to apply 50 pounds of force to this table, does that tell the whole story? No, what else do you need to know about that? Yeah, which way I'm pushing. Am I pushing straight down? Am I pushing this way with 50 pounds? Am I pushing towards you? Sometimes that's what I want to do. Okay? All right? So force. Momentum. Okay, momentum is a type of quantity. It has direction, the direction of momentum. Okay, so then we have to talk about, so displacement is a change in position. So from where I am here to when I exit the classroom, go out those doors, that's a vector because it has an amount, how far, and a direction. So I could go that far from here to those doors in many different directions, right? So displacement combines both how far you go and the direction that you go. Just how far you go is called distance. That's a scalar. So if you're just talking about distance and direction is irregardless, then that's just a scalar. So if a car goes around a track and how far it went, regardless of the turns and starting point and ending point, just how much the odometer turned, right? How much distance was covered, that's scalar. And then similarly, Velocity is a vector. It's the speed along with what direction that you're going. And so then the speed, how fast, regardless of direction, would be the scalar quantity. Okay, so when we talk about distance traveled, the implication is that's a scalar. Direction doesn't matter. But when you talk about displacement, then you're putting both together. That's a vector, both how far and direction. Same with velocity and speed. Velocity is our vector quantity, includes direction. Speed, how fast, doesn't include direction. Okay, does it make sense? All right, so how do we represent vectors? They're represented with arrows. Okay? And so naturally, the direction of the arrow is pointing for the direction of whatever quantity you're talking about. Okay? And then the arrow's length corresponds to the magnitude. Okay? So which one has the greatest magnitude? Obviously, A, B, C, or D? B. Okay, B is the longest vector, so it has the greatest magnitude. C, just from a relative side, then has the least magnitude. Okay? All right, and then the arrow showing the vector has a tip and a tail. All right, so the tip is the direction of the point. The tail is like the starting point. Okay, so I don't have this on here, but we want to talk about polar representation. All right, so polar. So when you write a vector, you use, what are those called? What are the names of those? Those things, okay? As opposed to a point. So don't get vectors confused with a point, which we write this way, right? X comma y. So this is indicating that we're talking about a vector, which is some quantity that has magnitude and direction. And so magnitude we call r, and direction we're going to use our standard angle theta, with the angle swept counterclockwise from the 3 o'clock position. That's why we need a trig first. Okay, we need trig first, or we can do vectors. So this is the standard angle. Swept counterclockwise from 3 o'clock. R then is the magnitude of the vector. Okay, and so let's call this, we'll call this 2, just for reference. So I want you to, if that's 2, and then these all have the same scale, then I want you to write the polar representation. Shouldn't have wrote equals there. It's not. Polar representation. This is the form of polar representation. So go ahead and estimate the polar representation of all of these. So it's just estimating to see if you get it. So for each one of these, write it as r, its magnitude, comma, theta, which is our standard trig angle, swept counterclockwise from 3 o'clock position, and you're estimating all those values for these 4 vectors. Go. Just see if you get it. Oh, use degrees, okay? Use degrees. That's most common. When you talk about vectors, it's most common to report that angle in degrees. Okay, and then compare with the person next to you. See if you're in the ballpark. Everyone's going to have slightly different answers. Okay, Fahia. For A, what's the angle that you estimated for A? What did you say? She wants 120 degrees. Ballpark? Decent. 120, 130, something like 120, 130. So we'll say 120, that's fine. It's a little, but it's not quite 135. Can you see it kind of points more up than it does halfway? So I'd say 120 to 130 would be good. All right, B. Let's see here. Divi. What'd you say for the length relative to this being 2? 4, okay. Angle?
260.
260. How do you do? Yep. Okay. C. Christian.
I said 0.5.
0.5, like 1/4 of that. I think that's good.
And then about 70.
70. That's a little stout for 70. It's maybe a little bit more than 45. I'd say 45 to 50 or 55. 70, a little more. Too much, but we'll say 50. Actually, it could be more than that. It could be closer to 70. It could be 60. Is that right? That's right? 60 is right. Yeah, okay. Thanks for clearing that up. Okay. D. All right, so how about D? Go ahead.
I got 345.
He wants 3 and 345. So what is splitting the fourth quadrant in half? So if we split the fourth quadrant exactly in half, what would it be? What is that? 315? Is that right? And what did you say?
345.
He's at 345. Fair? Yeah, that's decent. Pretty good. Okay, so this is how we report polar representation. But the way that these angles are reported in like real context is different. They won't say 345 degrees. What they'll say is 15 degrees south of east. Because that's kind of a more streamlined version to get this direction. Instead of thinking, we got to go all the way around 345, where exactly is that? Is that closer to the bottom? So this is more like if you're talking about the heading of a plane. 15, so what's east? East is straight. East is, straight at the 3 o'clock position, and then we're going to go 15 degrees south of that. So do you see that that's kind of an easier way to communicate that direction than saying 345? Okay? So now I want you to, for the first 3, I want you to write what you think is the easiest way in this form. For the first 3, write what the angle is. What's the easiest way you think to write the angles for the first 3? Go. Use the numbers the estimates that I wrote on the board. Use those numbers, okay? We said 60. Okay, Lexi, what'd you put for A?
60 degrees north of west.
She wants 60 degrees north of west. Does it work for the first one? So if it's 120, here's west. If you go 60 degrees north of west, do you get that angle, 120 degrees? Yes, that's right, 60 degrees north of west.
Say 30 degrees west.
30 degrees west of north. Does it work? It also works. Both of those work, okay? So 60 degrees north of west, 30 degrees west of north. Okay, B. Let's see. Jonathan, how'd you do on B? So we want to use something close by. What's the closest thing there? So how can we do it in terms of south? So straight down is south. 10 degrees west of south. 10 degrees west of south. Okay? And then what about C? Let's see. Matt, this Matt right here in the black sweatshirt. 30 degrees east of north. What do you think? Yep. Or you could say 60 degrees north of east. Both of those work. Okay. Make sense so far? Anybody have a question? Okay, then symbolically, vectors you'll see written as either a bold letter, like here I've shown in the first one, a bold V, or just an italicized letter with an arrow across. And so when you're writing freehand on your paper, you're going to use the second choice, obviously. It's a lot easier. But in textbooks, in printed material, you'll often see them as a bold letter like that. But they both mean the same thing, representing the vector, either vector V, vector A. Okay, so equal vectors. So a vector has a specific direction and a magnitude, but doesn't have a distinct location. This is a key quality about vectors. It doesn't have a distinct location, but it does have that vector and direction, or that magnitude and direction. Okay, so suppose 5 people move, starting at different places. They start at a different place, they start at a different time, but they go the same distance and they had the exact same direction. So think of it like as an army troop, okay, or a marching band, or something like this. They all go the same direction, the same amount, same distance. But they start at different times, they start at different places. Because the vector is only magnitude and direction, they're all the same displacement vector. So d1 equals d2 equals d3 equals d4, etc. And so they're all just d. Okay, they're all just the same vector, because vectors are irregardless of where you put them and when they occur. Okay? Make sense? Okay, so I want you to give me a polar representation for D, an estimate for the polar representation of D, and this is 1, this is 2, this is 3. Estimate the polar representation of D. Go. And do the angle both as, so equals polar representation. Estimate it. Kenneth, what do you think?
1.6 at 45 degrees west.
1.6. That's 1 right there, like that. You're a little short. So 1 is like that. You see that? So that's a magnitude of 1, then from there to there is about 1. So he wants 2.6. In what direction?
45 degrees west.
Okay, but so when we write the vector, though, we're going to write that angle. So what would it be? So when you write the vector like in this form, you're not going to use the north of east, south of west kind of format.
135.
Yeah, it'd be the true angle swept counterclockwise from 3 o'clock. So if you got something like 2.5 or 2 to 2.5 and 135 degrees, that's a decent estimate for D. Any questions on that? And all of those are the same vector. All of those are the same vector. Okay, so adding vectors. So here's 2 vectors, A and B. So to represent the addition of vectors, place the arrows tip to tail. Okay, so I'm going to put the tip of B to the tail of A. And so what this is like is kind of like the easiest way to think about adding vectors is in terms of displacement vectors. You're at home. First you go to Walmart. And then from Walmart you go to the bike shop. Okay? And so the sum of those 2 vectors would be like going from home to the bike shop, because that's the end result, that you started at home and you ended up at the bike shop. So that vector is the sum of those 2. It's kind of like as the crow flies, from start to finish, as the crow flies. Okay, so the sum is a single vector that results in the same outcome as the original vectors applied in succession. That's what I just said. So that would be the vector B plus A. All right, what about A plus B? So changing the order, meaning from your starting point, execute A first and then B. So there's A and then B. So can you imagine what A plus B would be? Right there. And what happens? It's the same vector, right? You see it's the same vector. So that's the same vector. Same magnitude, same direction. So just like adding scalars, you can change the order. 3 plus 5 is the same as 5 plus 3. Same with adding vectors. If you change the order, you end up with the same vector. Okay, so another way to represent vectors that we have the polar form is component form. So vectors can be expressed as the change in their horizontal and vertical components. Okay, so this is the key right here. When you express vector as components, you're expressing changes. Changes in x, the change in x, and the change in y. So let's see how that works. So here's the vector u. What change in x do we have in the vector u? So you think about starting at the tail and ending up at the tip. What change in x was there? Just x. What change in x was there from tail to tip? They're saying -1. Yeah, -1. So that's how much x changed in the according to the vector u. And what about the change in y for vector u? +2, right? +2. So we can express polar form is one way to express vector u, but another way to express it is that x changed by -1 and y changed by 2. And that also expresses that same vector. Okay, so I want you to estimate, find exactly. So a really good estimate for change v in component form. What's the change in x of v and the change in y of v? Change in x, what would you say? Maria? What's that? She wants 4 for the change in x. And what about the change in y? Okay, 4, -2. Okay, so we also use that same notation as the polar form, but in this case, the meaning is no longer r and theta, but change in x, and change in y, which is a different way to express a vector. So v would be 4, -2. So when you're looking at this way of expressing a vector, you have to know which form you're looking at. Okay, so the nice thing about having it in vector components, it makes addition very simple, whereas in polar form, addition is not quick and easy. So if we wanted to add v plus u, we're going to put the tip of v on the tail of u. So now you can break it down into components. If v took you 4 to the right and then u took you 1 back, the sum x component will be 3. So your net change in x direction was 3, 4 plus -1. And what happened with y? V took you down 2, and then u took you up 2. Net change? 0. So the vector v plus u is 3, 0. So imagine if we had the polar form of that, It would not be quick and easy to figure out what the sum of v plus u is. But in component form, if you break it up into change in x and change in y, it makes it very easy to add vectors. And remember that the length of the arrow represents the magnitude of the vector. So now I want you to find, given that these are, again, change in x, change in y for v, change in x, change in y for u, I want you to find the magnitude of each vector v and u. Go, find the magnitude of each vector v and u. Can you do it? And this is a job for what? When you do the change in x and change in y, and that vector, it forms a right triangle, right? It forms a right triangle. If we want the length of the slanted side or the hypotenuse, what are we going to do? Pythagorean theorem, right? So this is going to be 4 squared plus equals. So magnitude is written this way. Like you could use absolute value, and that'd be squared, or double bar. You'll see some textbooks with double bars. They both mean the magnitude of v. So whether it's a single absolute value bars or double bars, they both mean the magnitude of v. And so then 4 squared plus -2 squared equals the magnitude of v squared. So what is that? Radical 20? Coming. There we go. So this was radical 20. What is the magnitude of v plus u? That's easier. What's the length of that vector? 3, right? It's just 3. If you change x by 3 and change y by nothing, you changed by 3. Don't need the Pythagorean theorem, just common sense. Because it's all change in x. Everything's change in x. So however far you go in x is the magnitude of that vector. Okay, so web work and written work for Wednesday, as normal.